Hello everyone, I welcome you all to this new lecture series. In this series, I am going to make a number of videos on theory of computation. So I hope you are aware about the term theory of computation or automata theory. This is very important subjects for each and every CS or IT students. This is a very fundamental course which is having a considerable weightage in GATE exam as well as in NET exam. So this lecture series is going to be very helpful for you if you are preparing for GATE or NET, or if you are preparing for your university exam also. So let's start the discussion. Uh, Now, what is theory of computation? What is computation actually? The computation, like to compute something. Let's say if you take any example of machines generally take some input, process that input and generate some output. So this conversion of input to output, we consider like there is something called computation is going on, right? So how the machines or computer or calculator or any other machine like washing machine or any other machine is performing some computations, this subject actually is about the theoretical aspect of that, right? So for this subject you can use these many of books. Like the very first book is written by KLP Mishra, and the title of the book is Theory of Computer Science and Automata, Languages and Computation. There's another good book written by Pullman Hofcroft, Introduction to Automata Theory. There's another good book written by Peter Lynch, An Introduction to Formal Languages and Automata. So any of these books you can refer. Uh, in most of the universities, the very first book you find out as the textbook or the second one, right? So let's continue the discussion. Now, what is theory of computation? It is a branch of computer science that deals with the study of algorithms, models of computation, and the limits of what can be computed algorithmically. So, because if you are a computer science engineer, before you start programming for a particular problem, we need to be aware about the nature of the problem. We need to understand whether for the given problem a computational model is possible or not. Okay, so this subject will help you to understand all these aspects. It seeks to understand the fundamental principles and capabilities of computers and the problems that can be solved using the computational methods. So this is going to be very important, because if we are not aware about what can be solved and what cannot be solved, how we can write an algorithm, what are the nature of algorithm, what are the possible formal machines are available, then it will be difficult as to have a good grasp in programming or any other subject, right? So let's try to understand the automation. What is automaton? Refers to a self-operating machine. You can correlate automaton like the automation. Okay, we consider a machine is automated which does not require human intervention. So, or maybe minimal intervention is required from the human. So that is, we can say, okay, this is automated machine. Okay, we just press a button and it start functioning. Similarly, there is a formal model we consider as automaton. So you can compare it is a kind of machine or any device performs a specific task, right? Or functions with little or no human intervention. So this is important. It is often used as a general terms to describe any mechanical or electrical or electronic system designed to automate a particular process. Okay. The concept of automata can be traced back to ancient time. That means in the very ancient time also we were, or humans were using machines, those we can compare with automata. Like we were having the water clocks or mechanical toys at very ancient time also. There were different devices. They were also functioning as automata. However, in modern terms, automata typically refers to devices that use a combination of mechanical, electrical, and computer components to perform complex actions. Okay, so in a very abstract manner, if I want to represent the automata, it look like, so there is a, let's say, a device or a box automata which takes some input like I1, I2 till IP, and it generates some output like O1, O2, and let's say OQ, where P and Q may not be same or may be same, right? And there are certain number of states Q1, Q2 till Qn. Okay, so you consider once the input has been taken, once the input has been taken by the automata, it process, and once this input will be processed, the machine will transit to n number of states. So these states, there may be n number of states like Q1, Q2, Q3, and so on. Okay, so what is the concept of all this? How a machine can transit? All these things we will discuss one by one. Now there's a term we consider. Automata is also considered as finite state machine because automata generally have finite number of states. So when I represented here, there are n number of states. That means n is finite. Okay, it cannot be infinite. So the states must be finite in number. So what is a finite state machine? It is a mathematical model. It is a mathematical model, or you can say formal model, used to describe systems or processes that can be in a finite number of states and transition between those states based on input. So there are finite number of states. System or automata or finite state machine will take input from a very initial state and then start transiting the states based on the input, and then it convert or generate some output. Okay, right? Finite state machine are widely used in various fields. It includes like computer science, electronics, control systems, and software engineering. So there are multiple places we use finite state machines. Now, when we are talking about finite state machine, we need to be very particular about what is the definition of a state. So if you have already studied the AI or artificial intelligence, in artificial intelligence also, we discuss about state transition diagram or state space search. So what is state? What is state space search? You must be familiar by taking the reference of AI that when we are trying to solve a problem as a machine, that problem we need to define in a formal way. So let's say if I take the example of tic-tac-toe. So the game you are preparing and machine want to play, you want to prepare an automata. First we need to clarify the game. Okay, so the machine must understand the game in a formal way. So if there is a board which is having 9 squares or places, then as a computer science engineer we may take a data structures, maybe an array of 9 places, right? So step by step we need to define each and everything. Once your machine will understand the state, then based on the input the state can be transited. Okay, so here what is the state? A state presents a particular configuration or condition of a system being modeled, right? So in case of tic-tac-toe, first we need to clarify the state. So if I'm saying, let's say you are defining a state as an array, or I'm saying there's a character because I'm filling some characters here, and state is a character array which is having 9 places. Okay, so this can be the formal definition of tic-tac-toe board. If it is 3 cross 3 board, 9 total boxes are there. Now we need to define it, because why I'm taking character here, because I'm filling character value. So in tic-tac-toe generally we fill either O or X, or it can be blank also. So this is blank is also a kind of character. If we represent, there are 3 possibilities. If we don't want to represent like this, we can map these possible values with some numeric value. Let's say this can be represented as you can say 0, this is 1, or this is 2. Then instead of defining character, we can define as int, and we can put some restriction that out of these places either 0, 1 or 2 can be stored. So initially when the machine will start, all these places will have 2 if blank is representing. If blank is representing 0, then initially all these places will be filled with 0. Okay, so I hope what is state for a machine, this example can help you to understand. So to define a state for any problem for a machine, we need some data or some data structures. Okay, or we can define in terms of mathematical model also. Now let's take an example of 4-bit serial shift register using D flip-flop. Now you know that flip-flops are capable to store 1 bit. Okay, so if there are 4 flip-flops we are using here, then there's a 4-bit sequence, and if there is a 4-bit sequence, this is shift register, we can consider it is an automata. So if it is an automata, it must be having some number of states. So how many states this automata will have? It depends upon how many flip-flops we are using. So one flip-flop represent possibly 2 values, like it can be having 0 or 1, because it can store 1 bit. One flip-flop can store 1 bit data. So because there are 4 flip-flops and there possibly 2 values can be represented by, so all these 4, that means there will be 2 to the power 4 possible combinations. So there will be 2 to the power 4 or 16 states possible in this automata. Okay, and these states will be like, if there are 4 bits, they can be 0 0 0 or maybe 0 0 0 1, 0 0 1 0, and so on, dot dot dot, and finally all these I represent like 1 1. So in that way you can represent the 4 states in this. Okay, it accepts some input and generates some output, right? So this is one of the good example of an automata which is having finite number of states. Okay, now the description of a finite automata. When we want to define an automata, we need to define 5 tuples formally. So these 5 tuples are like symbolically you can represent like capital Q, then the summation, the delta, Q0 and F. So what does this Q represent? Q represent the finite non-empty set of states. So this capital Q represent the total number of states in which your machine or automata can be at any point in time. So if this automata is finite automata, this Q is a finite set. Then the next is this summation, which we consider as input. So it is saying it is a finite non-empty set of input called the input alphabet. So this is input alphabet. The meaning is, let's say if you consider an automata, let's say a calculator. Calculator is also a kind of automata. It is following in background. Now, if I ask what is the possible input for calculator, your calculator is or your computer is having some number of keys. There are some number of fixed ways by which your automata can start taking or your machine can take input. So if I take a very small example of calculator, calculator will have some of the key like 0, 1, 2 till 9. It will have some symbol like plus, minus, multiplication, division, equal to, and so on. So all these keys will define the set of alphabet for your automata, which I am comparing with calculator. Okay. So whatever we can press as an input, those symbols will comprises the set of alphabet for an automata, which is represented as a calculator, right? So this is the set of input, and set of input need to be finite, right? Then the delta. It is a function which maps your input state and the input with a new state. So what exactly I'm trying to say here, if there is a state, let's say if this is your screen of your calculator, initially when you switch on the calculator, the initial it must be displaying or maybe displaying 0 here. So once we power on a calculator, it is having an initial state. Every machine has an initial state. Initially, let's say washing machine. Once we power on the washing machine will be in the initial state. So all the registers, buffers, or whatever the values it is having, it will have some initial value, maybe 0 or some other value, right? So like the calculator will have some initial state, but based on the given possible keys set of alphabet, let's say there is plus, some equal to, let's say 0, 1, 2, 3, and so on. The keys are there in the calculator, and whatever we can press and give input, that is the set of alphabet. So initially it is in, let's say, Q0. Now when you are pressing, let's say 1, the state will be different from the initial one, because initially this particular screen is displaying 0, and definitely there has to be some register here which is storing this value. So this register, when you are entering 1, this register value will be updated to 1. Let's say there may be a number of registers we are using here, so it will change or transit its state from Q0 to Q1, like symbolically. So this transition will be defined by a function, that is delta. So delta maps what is the initial state or what is the current state of the system. So that current state can be defined by Q, and the combination of Q, this is the Cartesian product I'm saying. Q is a set, and this alphabet is also a set. This is also a set, right? And this is the Cartesian product. That means if this set is having n values and this set is having, let's say, m values, this Cartesian product will give you n cross m possibilities, possible combinations. Okay. So any of the state, any of the symbol will give you some new state, and that will also belong to Q only, because all these states we have defined inside this Q. Okay. So I hope this function you can understand. It is not very difficult to understand. Later on, you will get the clarity on this. Now, this is the function which describes the change of a state during the transition. Okay. This mapping is usually represented by a transition table or a transition diagram. So we'll see later on what is transition table and what is transition diagram. Now there is another tuple, that is Q0. Q0 is the initial state, and Q0 belongs to the set Q, because Q0 is also a state. It will belong in the capital Q, which is representing the overall state of the automata. And then one more tuple is, that is capital F. Capital F is also belongs to capital Q, but the capital S is the set of final states. So in automata, there may be n number of final states, but there has to be at least one final state. So in automata, there'll be only one initial state, but final states, there should be at least one. Okay. So this is the uh, introductory part of an automata. So I hope this is sufficient for the very first introductory lecture. The next session onward, we will discuss the automata theory in detail. So thank you everyone for connecting. I am just closing this session here. See you in the next class.